Let us discuss a few special properties of eigenvalues. If A is a square matrix, then the transpose of the matrix A also have the same eigenvalues as that of A. Next property says that if A is a square matrix having eigenvalues lambda 1, lambda 2, etc. lambda n, and the eigenvalues of another square matrix B are lambda 1 dash, lambda 2 dash, etc. lambda n dash, then the eigenvalues of the sum of the matrix A plus B will be given by lambda 1 plus lambda 1 dash, lambda 2 plus lambda 2 dash, etc. lambda n plus lambda n dash. Lambda 1, lambda 2, etc. lambda n are the eigenvalues of a square matrix A. Then, to find out the eigenvalues of k times A, where k is a scalar quantity, we just have to multiply k to each of the eigenvalues of A. That is, the eigenvalues of k times A will be given by k lambda 1, k lambda 2, etc. k lambda n. The eigenvalues of any triangular matrix are just the diagonal elements. That is, if you are given a square matrix which is upper triangular or lower triangular or just a diagonal matrix, then the eigenvalues are nothing but the diagonal entries. If eigenvalue of a square matrix A is lambda, then the eigenvalue of inverse of A is 1 by lambda. Let's look at the proof. Since lambda is the eigenvalue of matrix A, we have the equation Ax equals lambda times x, where x is a column vector. When we pre-multiply this equation using A inverse on both sides, we have A inverse Ax equals A inverse lambda x. This can be rewritten as I times x equals lambda into A inverse x, because lambda is a scalar and it can be taken outside matrix multiplication. A inverse A is I, identity matrix. From this equation, we have A inverse x equals 1 by lambda times x. When we compare these two equations, we have 1 by lambda is the eigenvalue of A inverse. Now the property says that if at least one of the eigenvalues of the given matrix is 0, then it's sure that the matrix is singular. That is, if you find one of the eigenvalues of the matrix is 0, then it's sure that the determinant of the matrix will be 0. The converse is also true. That is, if a matrix has determinant equals 0, then it's sure that one of its eigenvalue will be 0. Another interesting property is that corresponding to n distinct eigenvalues for a square matrix, we always obtain n linearly independent eigenvectors. But if two or more eigenvalues repeat, then we may or may not get linearly independent eigenvectors corresponding to the repeated roots. Another property is that if A is a non-singular matrix, that is, the inverse of A exists, then A inverse B and B A inverse have same eigenvalues. Similarly, if A and B are non-singular matrices, that is, A and B have non-zero determinant, then their products AB and BA have same eigenvalues.